All right. So purpose of this lab, guys, is that we want to investigate the relationship that we've been looking at here over the last, about a week or so, and that is that force times distance equals work, which also equals a change in energy, although we won't really be dealing with this part of it in this lab. We're mostly going to be looking at the force times distance equals work part of the work energy theorem. In this lab, we have another lab that we'll do next week probably, where we'll look at energy conversion, and we'll look at the change in energy part of that in that lab. Okay, so that's the one we want to look at. Looking at that formula, okay, if I increase the force, what'll happen to the work? It'll increase. Same with the distance. If I increase the distance, work will increase. Okay, so then what we should get here is another linear relationship on a graph. Okay, that is, if I double the force, I would get double the amount of work. Okay, we should get something like that, okay, according to the way this formula is set up. So that's what we want to investigate. So the lab's going to work like this. You are going to have a rubber band, and you are going to put it between the legs of two desks. Okay, so the back leg of one desk, the front leg of another. They need to be fairly close together. Okay, you can't stretch obviously this single rubber band across the front two legs or even the back two legs of a desk. Okay, there are a couple of sets of rubber bands in there that are actually two rubber bands tied together. You might be able to make those go across if you got a set of those. Okay, but what we're trying to find out here is what happens to, like if we exert a certain amount of force or pull this a certain distance, what happens to the force in the rubber band? All right, so we're going to put this across the legs, and we're going to put a ruler on the floor. Right, we're going to pull the rubber band to certain distances, and then we're going to record the amount of force needed to pull it that far. Okay, so we'll have a ruler, this rubber band, and we'll have a spring scale. Okay, so the spring scales, okay, and we want to use, there's two different kinds in the box. Okay, there's 2,000 gram ones, and there are 500 gram ones. You need the 2,000 gram ones. Okay, if you grab the 5,000 or 500 gram one, you'll pull it and it'll max out right away. Okay, so we don't want to use those ones, just the 2,000s. So a spring scale looks like this. Okay, in fact, I have a picture of it on the next slide. Okay, so we got, okay, our spring scale here. Okay, you can see in the back here in the workings, there's just a spring. Okay, and then we have this, the meter here on the front. Now, problem is that we need these to measure force. And on the front of these ones are grams and ounces, neither of which is a unit for force. This is the problem. We tried to tell Boreal Scientific that when we ordered these and got them, and they're like, we said, the box shows a picture of a scale that has grams and newtons on it. That's what we ordered. And they're like, uh-huh. And we're like, what's in the box is not what's on the box. It's totally different. And they wouldn't take them back. Thus, we have never ordered anything from them again. Customer's always right. Remember that. Okay? If you ever go into business, customer's always right. We were obviously also very right in that this is not what we ordered. But, okay, it's not a really hard conversion. Okay? All you're going to have to do is take whatever it reads in grams divided by 100, and that'll give us the newtons. It's approximate, but it's close enough for what we're going to be doing. Okay, so if it says 400 newtons, or 400 grams, sorry, it's 4 newtons. Okay, if it says 600 grams, it's 6 newtons. Pretty easy conversion? All right, no problem there then. Okay, we won't tell Boreal Scientific that, but yeah. All right, so we're going to have these as our distances here. Okay, we're going to pull the rubber band to 5 centimeters, 10 centimeters. We probably won't be able to pull it this far. Actually, we'll probably have to use different ones. We'll decide what they'll be here in just a sec. Okay, so for our variables here, okay, we're determining the distances, which makes distance the manipulated variable. All right, we're deciding what the distances we pull the rubber band to will be. Okay, and we're going to be measuring what? The force required, which would make that the, okay, good. Now, you've got to come up with 3 controlled variables, okay? Now, I'm going to tell you a few things about doing the procedure. If you listen carefully, you'll probably catch all 3 of your controlled variables while I'm doing the explanation, okay? So, when we do this, okay, we are going to have a single rubber band. We are going to place it around the legs of these 2 chairs, or 2 desks. You're going to need to have at least 4 people in your group, because 2 people in the group need to be ballast. They have to sit in the desks and make sure that the desks don't move. Because if the desks move, they will stretch the rubber band more than it was when you started the experiment. Which means now when you pull on it, you'll pull harder to make it go the same distance you did before. We want the tension in the rubber band to stay the same throughout all the trials. Okay. Do we want the rubber band to stay the same? Like if this breaks, what do you have to do? You got to start over. Okay. I mean, all of those rubber bands should be manufactured to the same specifications, but we can't be sure. And I don't know if somebody, ran out one day and put more rubber bands of a different kind in the bag. So I can't guarantee that all the rubber bands are the same. So if you break one, you'll have to start over, okay, so that you can ensure that all of your data is nice and linear for the same rubber band. Okay. When you are looking and measuring, where should you look from? Because we're going to have this set up on the floor. Yeah, you want to look perpendicular. You want to look straight down on the ruler. If you're looking from the side or at an angle, you bring in something called parallax, okay, which means the angle you're looking at makes you misread the reading on the ruler. So you need to make sure you're looking kind of straight down at it when you are pulling the rubber band. Okay, so things like that to make sure of while you're doing the lab. We also want to make sure we're pulling straight. Okay, if you pull to the side at all, we start bringing in vectored forces. We don't want that. Okay, we want to make sure that our direction of pull is nice and straight. When you set this around the desk legs, make sure that when you pull it with the scale, you hook both sides of the rubber band. Okay, you want to pull it like this. Okay, not just one side, you want to hook both sides of the rubber band when you start pulling it. Everybody with me there? Okay, you're probably not going to be able to pull this like, so there's 2,000, that's maxed out. I wouldn't say that's much more than about 15 centimeters. All right, I'd say 15 centimeters is probably the maximum that you're going to be able to pull this thing before you max out the scale. Okay, so if we're looking at our chart here, okay, for our distances, we've got 6 spaces and we need to get to 15. So I would say maybe start with well, start with 0. We can go up by 3. That'll only get us 5, though. Well, yeah, if we start with 0, you're right. No, then we'll get up to. All right, let's do it that way and hope that 15 doesn't max it out too much. So when you put the rubber bands along or between the legs of the desk, the rubber band has to be taut, not like stretched, just so that it's not hanging. Okay, so just enough that it's taut. That's the position you want in or condition you want it in when you first start the lab. Okay, hypothesis. All right, so in our hypothesis, we want to have a hypothesis that explains how we could calculate the work done on the object. So in the if part of our hypothesis, okay, we want to talk about force, distance, and work. Okay, we want to talk about the relationship there. So the if part needs to talk about the relationship, and we already said it was what kind of relationship? Okay, so talk about that, okay, between force, distance, and work. And then the and part will describe the experiment, the same as it always does, okay? The then part needs to be how you're going to calculate the work done on the rubber band, okay, using a force distance graph, because you're going to make a force distance graph in this lab. And the instructions for how to calculate the work using said force distance graph may even be in the analysis questions. So it might be like a really easy then part if you read through the directions in the analysis. It may tell you exactly how to do it. You'll have to explain a little bit, but that's it. Okay. All right, so the procedure for the procedure and observations, we're not going to obviously use these measurements because we've already said we're not going to be able to pull the rubber band that far without maxing out the scale. So we're going to go 0, 3, 6, 9, okay, go up by 3 and record our forces for that. Record those in there and then in Google Sheets, okay, build the graph. I didn't even include a Google Sheet this time because you guys can just open up a Google Sheet, make your own graph, paste it into the report. Okay, you don't need to have my template in there for that. Okay. Then for the analysis and interpretation, okay, perform the calculations they ask for there. I would say ignore this part though, okay? Do it the way they talk about in the first part, okay? Right, so up here where it talks about half the base times the height, okay, that's the way to do it. Okay, don't use this average part, even though it's the same thing, it's more confusing. All right, then number 2, okay, you need to tell us what the area under the force graph represents. Okay, so when we do this calculation, we calculate that area. What is it that we're calculating? Give some explanation, okay, because that's how do you know, all right? So give a little explanation on that. Conclusion, same as always, copy paste your hypothesis, look at your data, were you able to calculate work in the way you said you were, okay? And then evaluation, your sources of error. Ethan. Pardon me? Yeah, I know, because you can use I gave you the PDF. Yeah. Okay. So you use this like in your thing here where it says work lab. Okay. If you click on this physics lesson 12, it's the same sheet I was just using up here. That's where the analysis questions are. Okay. They're in there. I didn't put them in the template, right? Because I knew I was going to give you this document. Sorry for the confusion. Okay. That's where you can find them there. Okay. All right. I think that's about it. I don't think there's much else to tell you. Okay, you just need to be mindful of the movement of the desks. Okay, make sure that the rubber band is taut. Make sure you're taking good measurements. Okay, and it won't take you long to get this lab done. Really, realistically, you should be close to done by the end of class today, because you just have to take 5 or 6 measurements and then you're finished. All right, so I will grab the meter sticks. Okay, spring scales and rubber bands are over on the table. I'll put the meter sticks over there, okay, as well. Grab what you need and you'll be all set.